All right, well, good morning, everyone, to another lecture on discrete mathematics and applications part 1, 2020 McMaster University, or at least wherever you are. I hope you're all enjoying the beautiful snowstorm this morning. Somebody's having breakfast. Enjoy. So this, we put up the slides already before lecture, so you should all have the slides. Who would like to be the person who says hello occasionally? Just to make sure I'm not talking to the void.
Maybe you can be the person who's doing dishes.
I don't know who that person is. Is it Ganhoon Park? Park, is that you?
Oh, sorry.
It's all right. What about Tammy? Tammy, are you here still?
Hello.
Oh, Tammy, do you want to be the person that embodies the rest of the class? So I know I'm not talking to the void.
Yeah, I can do that.
If you don't want to, that's totally understandable.
No, I'm good. I'm good.
Okay, I would just feel empty inside. At least when someone's talking to me, I feel like we're having it's almost like a classroom.
Yeah, mathematics.
Mathematical, algebraic, trigonometric.
Yeah, I got this.
Thanks, Tammy.
No problem.
I forget who it was yesterday. Someone asked about monotonicity and instantiation. So let's try to make it there today. I hope no one steals control from me. So I won't repeat some of the stuff from yesterday. The other class needs to get caught up on a little bit. So the slides some of it is repeated for them. So just quickly, for those of you who weren't paying attention yesterday or may have forgotten, calc check, very, very similar to what's going on in the textbook. Very similar. The only way to really get comfortable, so a lot of people have been emailing on how to do well in the class, is really you can't really learn a new language without practicing it often. If you really want to learn French, you got to practice it often and get feedback on what you're doing is correct or not. And that's what CalcCheck gives you, quick feedback. It's unfortunate, but when sometimes people are busy, they just try to get that delicious looking green and don't really know what's going on. So please make use of the numerous channels we have available. If you want me to make a new channel, just let me know and try to ask, try to figure out what's going on. And we are working on some solutions. So hopefully they'll be posted soon. Okay. You should definitely be familiar with all of these words by now. If you're not, I really advise you to become familiar with them. If you don't know what they mean or you're struggling to understand some of these concepts, please reach out. The course help is there. And the book is an absolute delight to read. Okay, ducks. So we talked about positivity yesterday. I just want to remind you that there's a little tiny dot between the word pause and the argument. This little tiny dot is what the book uses to indicate function application. Okay, so we don't write that little dot, but I just wanted to let you know that this is what the book does. For example, we write the negation and then the argument, whereas the book likes to use a dot occasionally. So just in case you're reading there and getting a bit worried about it. Okay, so we talked about case analysis, and some people were curious about completeness. So we're going to talk about conditionals hopefully next week in programming, and then the issue of completeness will come again. Let's have a little pause. Is anyone interested in talking about case analysis and how it applies to programming? Can I hear a yes or a no from at least 2 people?
Yes.
Sure. Yes.
All right. Was that one person or multiple people?
That's 4 people.
All right. Well, somebody clearly knows what's going on here, so I'm glad. All right. Case analysis and programming. If it's too small for you, please let me know and I will try to make it bigger. Okay. So many of you have already seen case analysis. Some of you, for example, want to become Android developers. That's pretty fancy. And then you might work with a language called Kotlin. So Google announced that their primary developing language for Google, Android Google is going to be Kotlin. It's like Java, but better. Okay. Now, when you might start using Kotlin, you'll see something called a when construct. It's like an if, but with multiple branches. So let me use this notation. If C sub 0 goes to S sub 1, and then we'll have this OR symbol, C sub 1 goes to S sub 2, and then with C sub 2 goes to S sub 2, 1, 0. And we'll have a bunch of dots, and we'll say with C sub n to S sub n phi. Okay. So let me just use this generic syntax. This is known as the guarded command language. Guarded command language. The idea is you will see it in Kotlin, you'll see it in Haskell as patterns, you'll see it in Lisp as cond. So this idea of having multiple branches, all right? So this is multiple branching if, right? So how this works is if any condition C sub I is true, randomly pick the corresponding body S sub I and execute it. Otherwise, none of the C sub I are true, crash. Okay. So the way that, so in general, you can have, and these multiple conditionals are really old. If you work with assembler, for example, you'll see conditions. Is this number equal to 0, greater than 0, or less than 0? And then you perform an action correspondingly. So how this works is we look at these conditions. If any one of them is true, we randomly pick one of them and then perform the corresponding statement. Now, if none of them are true, the system crashes. So for this statement, for this program to be correct, we need at least one of the CI to be true. Okay. For this command to be correct, we need, this is completeness. Completeness, right? And that's where I got the name completeness originally, from this idea of programming, right? At least one of the possible conditions is true, right? i.e. C slash 0 or C sub 1 or C dots slash or C sub n, right? i.e. there exists an I of type natural numbers with 0 less than or equal to I, with I less than or equal to n, such that C sub I is true. Okay. So this is where the idea of completeness comes from. Many languages will have an if-else clause, and then the else means if this condition or otherwise not this condition. And so the completeness is given to us by the law of the excluded middle, which is what happens in this case. Okay. So we'll get to conditionals next week. We'll start off with binary conditionals, if then else, but I just wanted to let you know about these multiple conditionals, which you can see in popular languages like Kotlin as when, Haskell as guards. You'll see them in Lisp as cond, so they're very pervasive. Unfortunately, the C language family doesn't have them directly there, but even in Python, as long as you have a hash map, you can make these conditionals. Okay. And if you're interested, we can talk about it afterwards, and we can do some code if you like. All right. So let's continue our preview from yesterday. Is there any questions about this case analysis and programming? I don't want to make things worse. Does somebody want to say some words?
I don't think so.
You don't think this was misleading or that it was not leading?
I don't think it was misleading.
All right, I just want to make sure. So we might not cover this syntax. We might not get to it in this term. So we'll start off with binary and we'll see how people feel and we'll take it from there. So as I've been repeating, trying to get it home, small commutative monoidal operations have big counterparts. Okay, so these are the ones we're going to see predominantly in this class. But of course, any symmetric associative unital operation will work. Anything from a commutative monoid will work. Okay, dokes. So here is the example, and later when we get to conditionals, we'll find some generic rules for these. So right now we just say it's the unit, but we can phrase them even more so with the conditionals later on, in particular the trading rule. So, but just wanted to quickly go over these again. So we've talked about this stuff. The slides are here for the other class, so you need to get caught up. If you see something that you want me to talk about right now, please stop me and we can talk about it. The proviso right here is so that when you perform the substitution, you do not change the number of y's that occurs in the expression, because there are no y's, right? The dummy variable does not really matter. You can change y to apple or dog or XYZ, anything you like, okay? And this idea of changing them to any name you like is captured by alpha renaming or alpha conversion or dummy renaming. You can substitute equals for equals inside the body or inside the range, okay? When there's nested loops, you can unnest them. You can also take nesting and lift it up together, right? So these are common optimization techniques you'll see when you program in high-level languages such as Python or Lisp. They will allow you to do this kind of stuff. Other languages like Haskell will also allow you to do this. And then nesting is called currying. Okay, all right. You can, of course, change the order. All right. Not always available in some modern languages, but some things you can do. And here's the cases for all and for exists. We talked about distributivity. We said if you think of this syntactic part as the operation, then the syntactic part goes over Q and the syntactic part goes over P. And so essentially it distributes, okay? Because your operation is commutative, you can always split up the pieces and then perform some of them and perform the other, right? That's why we need commutivity. So this rule is also known as generalized commutivity, okay? We talked about range split, right? When you're doing some data streams, you can do some of them and then the others because they have no commonality. When they do have a commonality, you have to account for that. Okay, and this is where we left off yesterday. So hopefully that wasn't too fast, but I just thought it was useful to recap what we've been doing. For idempotent star, something interesting happens. So when it's idempotent, you don't need to worry about having duplicates, because if there's ever a duplicate, P and P, that just collapses into P. That's what it means to be idempotent. So if there are duplicates, it's no big deal. They disappear. In contrast, for addition, when you say x plus x, well, that's 2x. That actually matters. 1 plus 1 is 2. 1 plus 1 is not 1. So the number of times something occurs for addition actually matters. But for idempotent operators, it does not matter. And so we have this operation. And this rule is essentially generalized idempotency, right? We take the idempotency of an operation and we lift it to the quantification level. Okay, dokes? So this term that I've been using, this qualifier generalized, here's a really common one you'll see, generalized De Morgan. So you recall De Morgan turns ands into ors. Well, we said existence is just a bunch of ors, right? And then negation applied to or gives us negated ands. But we said ands are just the for all. And so generalized De Morgan says when you negate an existence, you get a for all, right? So this is where the phrase generalized comes from. You look at how things work without quantifiers and you realize, oh, wait a minute. If I do this, arbitrarily often in a quantification, in a loop, then I expect to get the same behavior. Okay, dokes? So these 918, these different forms are provable from this single form using double negation. Okay, so different forms of double negation will give us these other forms. Okay. Because of this reason, because of generalized De Morgan, some textbooks and some math classes like to define existence in terms of for all. They say when something exists, it means it's not the case that everything does not have that property. So they use this double negation to define existence in terms of for all. That's okay, but later on, and maybe we'll get to it in this class, when you think of propositions as types and types as propositions, this doesn't hold in general. It won't be an equals. So, but just wanted to let you know about it. And now we've gone almost full circle. So let me show you how this one works. So trading, here's the general rule for trading. So maybe we'll get to it later on. O plus X with R, and I have Q, okay, slash spot P, okay. So the general rule here is O plus X slash with R slash spot. Who knows what we can put in here? All right. Who knows what goes in the question mark? Let's have some interactivity. What should we try to do? In general, if you're looping over a range involving R and Q, and you decide, you know what, I'm just going to loop over R, you have to somehow account for Q. You want Q to also be true. So how do you account for that in the body, right? So for example, you can write a while loop, and your while loop has a condition, and then you can write a while true loop, and the condition is now accommodated for in the body. Does anyone know? So this is another thing from programming. Does anyone want to try it?
Would it be and Q? Like P and Q?
So someone suggested this. I think it might have been Casey. Someone suggested this. All right. Thunder? No, I don't have thunder. Slash bottom. Okay. So this won't work because what if P is a number? What if I'm adding the number 5 a number of times? And this won't work. But you're very close. Does somebody else want to try? Pretend you're doing programming. What would you do? How would you account for the constraint Q?
I'm lost on what's going on.
I'm sorry?
I'm lost on what's going on right now in South London. I don't understand.
So we're just trying to motivate this idea from programming. And in programming, for example, you would say, while 0 is less than I, and I'll just use this notation again, and n is not equal to n, we do x becomes f of x. We update x somehow. Okay. Well, this is essentially the same as writing while 0 is less than I. Here's what we do. We say if n is not equal to capital N, then x becomes f of x, right? Else do nothing, right? Also known as skip, and then we wrap up our loop this way. Okay. So notice how a condition in the we have a pair of conditions, and we moved one of the conditions down into the body. Okay. So we'll get to conditionals later on. I just wanted to motivate it. So don't worry if you're not comfortable with these conditions. Just wanted to get you ready for next week. So if Q is true, then we perform P. Else we should do nothing. So what's the nothing? Does anybody want to try? What's the do nothing for an operation called?
Is it the identity?
Yeah, way to go. Right? Doing nothing is called the identity. Right? And, right, whoa, look at this. Look at that. The identity of composition, right, sequential composition of programs, is the do nothing program, usually written as just white space in many languages. Okay, so many languages will, instead of calling it do nothing, the identity of sequential composition is just the empty program. Empty program. Okay, so I hope that's so we're still in the realm of loops. I just want to show these are the majority of our general rules, and today we'll talk a little bit more about them if anyone's interested. So let me. Would anyone like to see a proof of any of these theorems right here? Just for show. Would anyone like to see any of these, or should we move on?
Yes, please.
Do you want to pick one that you like?
The third one.
The third one. There's a lot of 9.3, but I'm assuming you're saying 9.3c.
9.4c.
9.4c. Okay, let's try proving that. 9.4c. 9.4c says for all x with for all x with q and r, we have p, and we want to show at the very end that for all x with q, we have, where's 9.4c? R and P equals R. R and P equivales R. Okay, so I'm just going to show it to you here, not in real calc check, just to avoid having to worry about all the technical details, such as where's my cursor? Okay, so the very first step, all right, the only thing we can do is we want to move R from the range to the body. And there's only one rule that lets us do that, namely the trading rule. It lets us trade R from one side to the other side. But it says trade everything. So all right, let's trade everything. All right. So we'll say for all x with, we're trading everything. So Q and R now becomes an implication, P. Okay, this is by trading. Well, this is close to what we have, but we really don't want Q beside us. So we want to get rid of that Q. Well, the only way to get rid of something from here to the other side is to use trading again. And trading says it needs to be an implication. So let's try to make this into an implication. How do we take this and turn it into an implication? Well, there's only one rule that lets us shunt R to the other side. And that rule is called, unsurprisingly, shunting. Right? Spot Q implies R implies P. Shunting. Okay. Then now that we have this shape where it's Q implies something, we can use trading again. And so we can say for all x with Q spot R implies P. We're really, really close. Does anyone see the last step? This is just definition of implication, right? R implies P means R is less than or equal to P, means the minimum of R and P is just R. And so we're done. Okay. Now the real challenge is get this working in CalCheck. All right. So are we good? Boop, 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 beep, beep. All right. So they're all really easy. All of these, like 9 ABC, they're all really easy to do. I recommend just for practice trying to do them on your own. Try to do them just by themselves, on a piece of paper. And then if you get stuck, try to consult the book, look at the slides, look at these videos. And then after you're comfortable with it, then try doing it in CalCheck. So try to do it in stages. Okie dokes. All right. So the trading rule, notice it follows from this general one, right? For all, well, it says if the thing, otherwise the identity of and. The identity of and is true. So if the first one, then do the second one. Otherwise, just return true, right? But that's exactly what an implication is, right? If this one is true, great. Then check P. If this one is not true, well, that means it's false, and false implies anything, and so the whole thing is true. So later on, we'll prove these kind of theorems. So let me just write that down for you. So later on, we'll prove that R implies Q, sorry, R implies P is the same thing as if R is true, then check P. Else, we want the identity of and, which is true. Okay. So later on, we'll actually prove this as a theorem. Okay. The proof is not very hard, but the cool thing is, because of the setup you have so far under your belts, you'll be able to prove this without too much difficulty. All right. And so again, this is another useful thing. If you ever see this kind of phrase in your programming, you know it's just an implication. And likewise, we can do for all. The trading for all becomes a conjunction, and it's another similar rule like this. Okay. So hopefully you see trading is a very useful feature. So let's move on to instantiation. It's a big one. And again, the slides are posted online already, and they usually are posted afterwards. So let's talk about instantiation, since some people were very interested in that yesterday. Let's in particular talk about the proof. So let's start at the very top. We apply 1 point rule to turn it into a for all. Then we weaken the range, right? So this part right here is called the range. We weaken it, right? So x equals E is weaker than true or x equals E. Okay. No, notice this is the opposite of what you might be thinking. You might be thinking, wait a minute. If I have A, then A implies A or B, right? But for quantification for all, it flips them around. So it's called range weakening, and it's the opposite direction. Okay, ducks. So we'll get to that in due time as well. So don't worry too much about it. Now that we've made it here, we know true or anything is just true, right? And then this is just an abbreviation, and so we can get it this way, right? And this is instantiation, right? And instantiation is just a generalized form of weakening. If I know this expression is true for P1, P2, P3, P4, then I know it's true for a P of anything I choose, right? If it's true for all of them, it's true for a particular one. This is weakening. Okay, next. In particular, in this class, we're talking about equations as much as possible, and using the definition of implication, you can always transform an implication into an equation. So if you're ever in the need to do equational reasoning, you don't need to work with implications. You can always get rid of them in favor of an equivalence. Just wanted to remind you of that. So here's an actual example. We have for all x, the successor of x is greater than x. Okay. So we're going to instantiate using 360, so this form, right? So that way it's still an equivalence, okay? Then we're going to apply the left monotonicity of and with instantiation. So we're leaving this part alone, and then this part we're applying instantiation to it. Okay, ducks? So we're choosing for x here to become y plus 1. Then we have y plus 1 plus 1 is greater than y plus 1, which is greater than y. So by transitivity, y plus 2 is greater than y. And of course, 1 plus 1 is 2. Okay, ducks? Does anyone have any particular questions here before we move on? Okay, ducks? Or not? Tammy? Casey?
I think no. I think it's all
Okay.
okey-dokes.
I don't know. I feel like you're all
Question.
secretly messaging each other, telling yourselves what you want.
Here's a question.
So here's with again, just in case you've forgotten. I've left it here. And, I'm sorry. Does someone have a question?
There's people asking questions in the chat.
I'm seeing nothing in the chat. That's strange. Huh. Let me
Oh.
check my mobile one. I'm not seeing anything there. Ah, there's 14 missed messages. I just saw it right now. Thank you for pointing that out. Apparently my mobile chat is up to date, but not that one. Okay. Yeah. So just quickly, yes. Where instantiation is a weakening for quantification. Okay. Yeah, nested loops. Okay, all right. So I have another chat here just in case. This one is for some reason not refreshing. So do let me know if you have further questions. Okay, next. So just quickly reviewing how with works. All right. If you have a theorem that says some premise implies some conclusion, and you know that some premise is true for some value x0, then when you say that theorem with a proof for that premise, that's the same thing as just getting the conclusion directly, right? It's like function application. If I have a function from A to B and I have a value of type A, I have a value of type B. Okay, so with is really just modus ponens. It's just function application. Nothing deep. Okay, docs. Okay, docs. Someone is asking about this y right here. Y is just any. It comes from this expression. If you have a multiplication involving zx and zy, then you can cancel that z to get just x equals y. So this works for all x, for all z, and for all y. Okay, dokes? Yeah, exactly. That's right, Eamon. It's just an arbitrary variable for the instantiation. Good job. All right. So sometimes you need to use nested steps. So up here, we said left monotonicity of and with instantiation, right? So how does this work? Well, we said the monotonicity of and lets us change this part. Great. All right, so it lets us have an implication. All right, so this whole thing becomes an implication. That's what the monotonicity says. And then it says the thing we want to use to get that implication is called instantiation 9.3, this theorem. Okay, so we're taking a complicated result and applying it. So let me write that down just in case that was sufficiently confusing. Okay, so 4.3 says if you have P implies Q, all right? So this is monotonicity of and. If you have P implies Q, then you have P and any value R implies Q and any value and any expression R. Okay, so that's what this one says. All right. So when you say monotonicity of and then you use the keyword with instantiation, what you get is the theorem. You get for all you get for all x spot P and R implies P with x becomes E and R. Okay, so notice that the with says, oh, hey, I have an existing implication. That existing implication is called instantiation. So please get rid of all of this because I have one and give me the resulting simplified theorem. The resulting simplified theorem is this one. Okay, now that I have this theorem, and this theorem is called monotonicity of and with instantiation, that's my hint right here. And I pick a value for E. Okay, does that help? All right. So here is the resulting setup in CalcCheck. So let's just go over it slightly one more time. We have our main theorem, and we're going to instantiate. And notice we're using 360, so the instantiation becomes an equivalence. Okay. Then we're going to perform a substitution. Remember, that's the caveat of using CalcCheck. You have to perform manual substitutions. So we replace every x with a y, right, on this expression. Then we use monotonicity of and with instantiation, which is this particular theorem, right? And that lets us down here. And of course, we have to perform substitution as well. Okay. So yes, in the book and in the informal calculations, there's always an implicit substitution. but in CalCheck, the substitutions must be made explicitly. Okay, next. And then finally, we get to transitivity, and we're using shunting, right, to turn, yes, we're using transitivity right here to get y is less than y plus 1 plus 1, and then we're just going to evaluate or use fact 1 plus 1 equals 2. Okay, next. The reason we're using left monotonicity specifically is because we're trying to remind you how monotonicity works, and we're just being careful that it's on the left. So here's P and R, and P is on the left, Q is on the left. So in an upcoming assignment, maybe, don't want to overwhelm you, there will be monotonicity only in one direction, but not in another. Okay. For example, implication is monotonic in one argument, but antitonic in the other one. Do you know which? Exercise. Try to figure it out. Implication is monotonic in one, but not in the other. It's antitonic in the other one. Okay. Transitivity of less than with shunting. Okay. So that's a good example. All right. So sometimes I'm not sure if I'm going too slow, and so yes, please continue to ask. So what does transitivity say? All right. So let's look at shunting first. Shunting says if you have P, P implies Q implies R, okay? That's the same thing as P and Q implies R, okay? Transitivity says A is less than B, implies B is less than C, implies A is less than C, okay? And then, where am I? Transitivity with shunting then gives us A is less than B and B is less than C, implies A is less than C. So you've seen these various forms of transitivity before, and this is just another form. That's all. Okay, looks. Alrighty then. So let's get to a bit more on for all. So let's try to wrap up universal and existential quantifiers for in preparation for conditionals. But please continue to ask questions if you have. Right? So this is called a meta theorem, and if you recall, the word meta means about. So this is a theorem about theorems. So we're saying the meta theorem says P, the statement P, just a term, just a statement, just an expression. This happens to be a theorem precisely when this one is a theorem. Okay, so if P mentions some free variables and you proved that one directly, then you can prove this one just as well. And here's the justification for this theorem. Suppose P is a theorem, then P is true, right? Because true is the identity of equivalence. So if we have for all xp and we know that P is true, then we can perform substitution and replace P with true. Okay, but wait a minute. If we're always talking about things being true, that's just true. And so this theorem for all xp is just true. For the other direction, for the converse, suppose for all x we have P. Now let's pick a choice for x. I'm going to pick x to just be the free variable that happens to have the same name, x. And now I perform x becomes x. So I go everywhere in this term, and every time I see an x, I replace it with an x. So I'm really not doing anything, and so I have P again. Okay. If you're not too comfortable about these meta theorems, it's okay. But the idea is that the meta theorems are what justify the relaxed syntax. So you saw that for any syntax? No problem, Nathaniel. Please ask more questions. I'll make many more of these empty boxes here for us to use. So remember when you saw the for any syntax, that's justified by the theorem. Right? To prove a for all statement, you just prove P for arbitrary x satisfying the range. Right? So to prove a for all x r P, you just say for any variable of that type satisfying that constraint, we can actually produce a P using that as an assumption. Okay. So we've seen this before, and the other class has, I think, zipped through this, and we're staying a bit slowly. Is there a theorem for where a quantifier is true if its expression is true? Yes, the one you're asking about is called 9.8. Okay, that Eamon is asking about. Okay, so this is what justifies why we're able to use for any. Okay, so when we started out, we didn't want to throw too many quantification rules or too many meta theorems at you, and we just said this is how you prove a for all. You do for any. But as you saw a moment ago, you can also prove a for all using just a bunch of equations, right? Equational reasoning. Okay, you can prove a bunch of for all expressions using equations instead of using for any syntax. Okay, next. Are there any questions right now? Yeah. Everyone's totally fine with everything. All right. Thank you, Jay. Yes, true for all body. All right, so this is finally the new thing, and now we'll get to more monotonicity stuff. So remember how we said instantiation, which is a word that I cannot spell apparently, is like generalized weakening, right? Generalized weakening, like P and Q implies P. Well, we have this thing called existence introduction, and this is also a form of generalized weakening, right? And that if you have a P, then you have P or Q. Okay, so remember we had two different forms of weakening, all right? So this is and weakening, and this one is or weakening. Right. You weaken an and by dropping it out. You weaken into an or by introducing it, right? Sometimes we also call this or strengthening, all right? And we write it as P provided, P or Q provided we have P. Okay. So existence introduction is this new theorem we're going to look at, right? Suppose that I know that P is true, but at every position I have a bunch of E's. Well, by the 1-point rule, I can abstract out all of these repetitions of E into an existence. So this is called a let clause. Okay, so you may have seen this in programming, right? So local definitions, right, are given to us by the 1-point rule. Right? So if you want to say, for example, let x equal E in the expression P, this is kind of like saying O plus X with X equals E spot P. Okay, so the 1-point rule gives us these local definitions, these let clauses. Right? I'm looping over all X that happen to be equal to just E. Okay. So this definition of let is very pervasive. You'll see it, for example, in terms of existence sometimes. Other times when you take advanced computing, you'll see it in so-called function definitions, right? This is a function definition. Given X, perform the body, and then substitute X with E everywhere, okay? So local or let clauses are a popular topic in computing, all right? So let's, provided is the converse of following. Remember, we have orders. Implication orders the Booleans, and converse is the other way around of provided, right? I am the father of Yusuf. Yusuf is the son of Musa. Okay, so the first it's me, then him, and then in the converse statement, it's him, then me. The order changes. That's what a converse operation is. Okay, so we're here. We perform a 1-point rule or a local declaration. That's what it's equivalent to. Then we perform weakening. Notice this time it's in the right direction, in the expected direction. If I have one piece, I can weaken it into 2 pieces, right? One or the other. This is 0 of or. This is just true. So this is almost exactly the same proof as instantiation, right? Whoa, almost the same proof, okay? We call E the witness that shows this is true. It witnesses the truth of this statement. We're saying there exists an X such that P is true. Which X? Oh, I know, the X known as E, that one. That one is what witnesses the truth of the statement, okay? It is very common to apply this rule as a strengthening rule. You want to show that this existence is true. So what you do is you say, all right, let me pick, let me select, let me choose a value for X. How do I make this true? Well, I'm going to choose X to be 1. Okay, and then this is true. So that's great. So this is how you use this rule. It lets you make choices, right? And why does this work, right? So if you recall, if you show that P holds because of true, that's the same thing as just showing true implies P, and that's the same thing as just showing P. Okay, so do you remember what theorem this is? This is the left identity of implication. Okay, so if you ever want to show that a statement is true, it's the same as showing that it follows from true. And so here we're proving there is a number X such that X squared is less than twice X. Okay, so there's a number such that the square of the number is less than its double, and this holds because we can choose 1 to be that X, and that one is true. Okay, let me just check. All right, I'm glad it helps. Please continue to ask questions. So the useful thing is it can also help us to find counterexamples. If you want to show that something is not true, this for all is not true, what we can do is to show a not for all, we rewrite it using De Morgan. Then we get rid of the quantifier altogether using existence introduction, which lets us make a choice, right? So I'm saying there is an X that such that twice X is not less than the square of X. And I can think of one, namely 2. So that's what existence introduction lets me do, right? And indeed, the double of 2 is 4, and the square of 2 is 4, and it's not less than, they're equal, in fact. Okay, so that's another common thing there. So we have 3 minutes left. I would like to talk just a bit briefly about the midterm, just to get you ready. This is last year's midterm, so I won't try to be too fast. I won't try to be too fast about it. Okay. So these were questions in last year. So we're saying there is an X such that for all Y, X minus 2 times Y plus 1 equals X minus 1, right? And here's another one, okay? And of course, because it's in existence, the first one, you can say, let me try to find a value of X such that for any Y, this is true. What value of X would we choose? That would make this always true. Does anybody know? Right. Maybe it's not true. Then we would look at this form. If we're looking at this form, well, we have a not, we can use De Morgan. That makes it into a for all, so we can use for any. Then the not goes here and turns this into an existence. And now we have to find if this is not true. Okay, so these are kind of questions we had before, and these are questions we might put in the midterm. Okay, so somebody in the comment says you can pick X to be 0 here, right? So this follows by having X become 0, right? Do I have time to play with it a little bit? I don't have time to put some in calc check, so we'll just continue talking about it a little bit briefly. So I mentioned not too long, so I just want to let you know these are questions you might expect to find on the upcoming midterm. All right, so and they're just applications of for any and existence introduction and De Morgan. Nothing sufficiently complicated. So just want to let you know right now. Someone mentioned, why are we talking about left monotonicity of operators? Well, we mentioned that implication, for example, is in the left, it's monotonic. If P implies Q, okay. Then sorry, in the right, if P implies Q, then right here R implies, and then R implies. I put the P, and then the P implies Q, so I can get the Q over here. But in the left, that won't work. right? If P implies Q, I don't have P implies R implies this one. I have it the other way around, okay? And this is the reason that when you get to the range rules for all, because for all trading turns into an implication, we end up with this kind of antitonicity, right? So even though Q implies Q or R, right? That's the weakening right here. One implies one or the other. Because it's antitonic, right? Because of the antitonicity rules, it happens the other way around when you stick it in a for all. Okay, so we'll get back to here maybe next week. We'll wrap up here, or maybe we'll cut this discussion short and not deal with it too much. I just wanted to show you how to actually use some of the stuff in concrete settings involving arithmetic that you might have seen. Anyhow, I thank you for listening to the Friday's lecture. And yes, the midterm is the week after next week. Every other week. Every other week? Every 2 weeks, there's a midterm. Anyhow, all the best. And if you have any questions, I'll still be here, and I'm happy to answer your questions.